Chapter 9, Trigonometric Identities and Equations. So we're going to sort of pivot at this point in our journey of learning about and working with trigonometric functions away from computational type problems like what we've been doing in the previous couple chapters, more towards kind of the theoretical analysis of trig functions. Okay, and we're going to start this by discussing the equals sign. Okay, so there's something kind of interesting about the equals sign. We're used to this as meaning equality, right? So this means equality, right? Whatever's on the left of the equal sign is the same in some sense as that which is on the right of the equal sign. But it turns out there are multiple types of equality that we deal with in mathematics. The first type is conditional equality. So, off to the side, I just want to make a note of this, like conditional equality. We see this a lot. An example of conditional equality would be something like this. Let's say that 2x minus 1 is equal to 0. Okay, so there's our equal sign, implying that we have some kind of equality here. 2x minus 1 is equal to 0. Notice that the truth of this, whether this is true or false, depends on the value of x, right? So we could figure out the value of x that makes this statement true by just adding 1 to both sides, dividing by 2. We can solve and see that x is equal to 1/2. Okay, so this is the value of x that makes this true, but any other value of x will give us a false statement, right? Like if I try to put in 0 for x into our original equation here, we would get -1 equals 0. Notice that that is not a true statement. So this is a very basic example of conditional equality, where we get a true statement only for a very particular value of x. Now there's another type of equality which we'll call unconditional equality. Okay, and unconditional equality is when, we might have some kind of equation. For example, sine squared theta plus cosine squared theta is equal to 1. Now there's a big difference between this equation here and 2x minus 1 equals 0. In this equation, it turns out that this is true for any value of theta. Okay, you could put in 0 for theta, for example. Like if we, over here, theta is equal to 0. So sine squared of 0 plus cosine squared of 0, this should be equal to 1. What is sine of 0? It's just 0, right? So this is 0 squared. What is cosine of 0? It's 1. Notice that this simplifies to 1 equals 1. Okay, what if I put in a different value of theta? How about theta equals, I don't know, how about pi over 3? Okay, well, sine squared of pi over 3 plus cosine squared of pi over 3, this should also be equal to 1. Okay, and then, thinking about the unit circle, sine squared of pi over 3 is root 3 over 2 squared, plus cosine of pi over 3 is going to be 1 over 2 squared. And supposedly this equals 1. Simplifying, we get 3 over 4 plus 1 over 4. We get 1 equals 1. Okay, so see how this unconditional equality is going to be true for any value of theta. Okay, so another word that we have for unconditional equality is identity. Okay, so when we're saying we're going to talk about trigonometric identities, they're going to be equations of this nature, where they're true no matter what the input is. Okay, so that's just a little demonstration, but here's the statement at the top of section 9.1 on verifying trig identities. A trigonometric identity is an equation or formula involving only trig functions that is valid for all angles. Doesn't matter if they're measured in terms of degrees or radians or for real numbers. No matter what the input is, we're going to have equality. So the first and sort of most basic identities that we have that we've already seen, the Pythagorean identities, so sine squared plus cosine squared equals 1, and these other two, which we can derive from the original 1 plus tangent squared x equals secant squared x, 1 plus cotangent squared x equals cosecant squared x. We have the quotient identities. These are just, basically the definitions of tangent and cotangent as sine over cosine and cosine over sine, respectively. These are identities as well. Doesn't matter what value of x you plug in, we're going to get a true statement from each of these equations. The reciprocal identities for secant and cotangent. It turns out the even-odd properties are also identities. Okay, so cosine and secant being even, the other four being odd. And then, we have basic arithmetic and algebraic operations, which are also identities, right? Like, for example, just to take a factoring example, remember this one? If we have a squared minus b squared, we can express this as a plus b times a minus b. You might remember the name of this identity. This is called the difference of two squares. This is another identity from algebra, right? And we use this all the time. It's really helpful if we're ever trying to factor something like, x squared minus 9, right? You know how this factors to x plus 3, x minus 3. Okay, this is just an application of the difference of two squares identity. Now, to get kind of warmed up for this chapter, the first couple examples we're going to do are going to involve just simplifying trig expressions. Now, what we'll do a lot of in this chapter is substitution, okay? And what I mean by that is, like, when we have identities, they give us opportunities to replace values in expressions or in equations with equivalent values, which might help us to simplify or modify or manipulate equations in ways that are useful. Okay, so for this first example, we're given this expression that's got kind of a lot going on. In the numerator, we have tangent t plus cotangent of t, and we're dividing by cosecant of t. Now, I expect there to be a much simpler way of expressing whatever this is. Let's see if we can use some of these identities that we have in the top half of the page to try and rewrite this in a nicer form. Now, one good strategy when we're trying to manipulate some expression in terms of trig equations or trig functions is expressing it all in terms of sine and cosine, right? Because everything kind of comes from sine and cosine. Tangent t I could write as sine of t over cosine of t. I can do the same for cotangent and cosecant. So let's start with that. So in for tangent t, like I said, let's write this as sine of t over cosine of t. And we'll be adding that to cotangent, which is cosine of t over sine of t. And in the denominator, we'll have 1 over sine of t, like that. All right. now that it's written in this way, you know, the path forward is a little bit more clear. At least I see, like, okay, I have fractions inside of a fraction, and I'm particularly drawn to this 1 over sine t in the denominator. I can just multiply by the reciprocal of that to simplify a little bit. So I might try this. Sine of t over cosine of t plus just copying down what I have in the numerator like this, sine of t. And I'll just multiply by the reciprocal of that denominator, which is going to be sine of t divided by 1, like that. And already this is looking a lot better, right? And I can now distribute this sine of t. And again, you know, like I didn't have any special privileged knowledge that told me to start doing this. It just, you know, you just have to pick something and go with it and see what happens. So distributing in that sine of t, I'm going to end up with sine squared t divided by cosine of t plus, and then I'll have cosine t times sine t divided by sine of t. And something nice happens here. Sine of t and sine of t cancel out. So now I'll have this sine squared t over cosine of t plus just cosine of t. Okay, from here, what can I try now? I do see that I have, you know, a plus sign between these two terms. I could possibly get common denominators and add these together and see if something nice happens. So how would I do that? Well, we have a denominator of cosine t over here, so I'm just going to multiply top and bottom of this over here by cosine t. So then I'll have sine squared t over cosine of t plus cosine squared t over cosine of t. And now that we have common denominators, we can just add the numerators together, and we'll have one big fraction that'll look like this. Okay, and you might be thinking, like, where is this going? Like, this looks worse than this does. You know, like, I think we're going in the wrong direction here, maybe. Now that I have a little bit of experience working with these trig identities, I'm actually very, very happy with what I'm seeing here. Mainly, I'm really happy to see this numerator. Sine squared t plus cosine squared t. This should look really familiar. This should ring a bell for you. This is the same as 1. Because remember, this identity that we were talking about up here and, you know, that we mentioned over here, sine squared anything plus cosine squared anything is going to be equal to 1. So I can just substitute in a 1 for that numerator. And that feels really good, right? Remember, we want to be looking for convenient substitutions that we can make based on the identities that we already know. So that is a really good one. Now I just have 1 over cosine t. What's another way to write 1 over cosine t? That is just secant of t. And that is about the best that we could hope for if we're ever trying to simplify some nasty expression in terms of a bunch of trig functions. If we can reduce it down to a single trig function like secant of t, that's awesome. Okay, so I'll box that up and that will be my answer. All right, so again, like I said, when I started this problem, I didn't know exactly how it was going to shake out. I just sort of picked something and started going with it. There could be many other ways to simplify this. Like there are definitely other ways that we could have you know, started this problem. You just got to pick one and go with it. So now we want to start talking about verifying trig identities. This is a process that we want to learn, a skill that we're going to be honing over the course of this chapter. What verifying trig identities means is, we'll be given some identity, like down here in example 2. It is being asserted that 1 plus sine of x over cosine of x is equal to secant x plus tangent of x. Okay, and this is being called an identity, meaning it should be true for any value of x. It is an unconditional equality. Now, how could we possibly demonstrate or prove to ourselves or to whoever's reading our work that these two are truly the same? There are a few different common strategies that we might use, but oftentimes we'll start with one side of the equation and manipulate it, simplify it, use some of the techniques that we just saw in example 1, and see if we could get it to look like the other side, right? Or maybe we'll start with the right side and see if we could get it to look like the left side. If it's really complicated, sometimes we'll do some work on both sides of the identity, both sides of this unconditional equality, and see if we could get them to match somewhere down the line. Okay, so some strategies that we might use, sometimes we'll start with the more complicated side. This is oftentimes a really good approach. Start with the messier side and simplify. Use trig identities. So for example, on this last problem, we started by rewriting tangent and cotangent in terms of sine and cosine. We did the same for that cosecant, right? So using reciprocal identities, if you see a sine squared plus cosine squared show up, you might want to replace that with a 1. So using trig identities to sort of manipulate one side of the equation. We could use common denominators, just like we did in this step up here, right? Remember, right around here, we decided to get common denominators of cosine to add those two together. That's something we might do. Factoring, multiplying by conjugates, these are just different things that we might be able to employ in this journey of trying to verify an identity. Okay, sometimes, we do all this stuff, it doesn't work out, no algebra tricks are working. Another strategy you might use is just putting everything in terms of sine and cosine, right? That's ultimately what we did in the previous problem in the first step. If things get too messy, sometimes you might have to start over and just try something different. It happens, okay? There's more than one path to the correct answer in pretty much all of these problems. So don't be afraid to just jump ship and try something different if you feel like it isn't productive. Okay, so let's look at example 2. Let's try this one out. We want to verify this identity. So let's maybe start with the messier side, whichever we decide that might be. Maybe you don't like the look of the secant and the tangent here. Maybe let's try and put that in terms of sine and cosine and see what happens. So the way I might start this is, let's start with the right-hand side. The right-hand side is secant of x plus tangent of x. Okay, and I'm going to work on this and see if I can get it to look like the left-hand side, which is 1 plus sine x over cosine x. So secant x, kind of a low-hanging fruit on these problems sometimes is, let's just write this in terms of sine and cosine. So this is 1 over cosine of x, and then tangent is sine of x over cosine of x. Okay, I'm feeling pretty hopeful about this because notice that this is already starting to look like the left-hand side of the identity. So what can I do from here? Well, I have common denominators, right? Let's try and add these two fractions together. So 1 plus sine of x will now be over a shared denominator of cosine of x. And would you look at that? That is the left-hand side. Okay, and once we've done this, we're done. I might just put a little rainbow underline showing that I got the left and right hand side to be equal to each other. Sometimes people like doing one of these little boxes filled in. That just means that we've proved the identity. And that went pretty smoothly. right? What if we had started with the left-hand side, right? Because I said that there's more than one way to do this. What if we started with the left-hand side and had 1 plus sine of x over cosine of x and decided, hey, let's start with this and try to make it look like secant x plus tangent of x. Okay, well, one thing that I might do just to try something is I can split up this equation, or excuse me, I can split up this fraction because I have this addition in the numerator. So I could rewrite this as 1 over cosine x plus sine x over cosine x, like that. And then I might recognize, oh, 1 over cosine x, the reciprocal identity tells me that this is just secant of x. And sine over cosine, that is tangent of x. And would you look at that? That is the right-hand side. Okay, so you also could have done it this way. Okay, so this is sort of like, or, you know, you could have done it like this. Okay, there's even a third way that you could have done this. I'm not going to demonstrate it, but maybe I'll let you play around with it and see if you could figure out what that is. Okay, so that's how these are going to go. This one was not too bad. We will see more complicated problems that require more sophisticated technique and solutions. But we'll just take this one example at a time for now. Let's look at example 3. We want to verify this identity. There is definitely more happening on this one. 1 plus sine t over cosine t plus cosine t over 1 plus sine t. Sorry, I don't know why that t got dropped off there. And apparently, supposedly, allegedly, this is equal to 2 secant t. Okay, I'm thinking I want to start with the left-hand side. Remember, starting with the more complicated side is oftentimes the better bet. So let's start with the left-hand side. And I'll write this out. And I'm thinking how I might sort of manipulate this left side of the equation and get it to be equal to the right. Now I'm going to leave a little space here because what I'm going to try is I'm going to try to add these fractions together by getting common denominators. Remember up there in that sort of strategy box at the top of the page, we saw that getting common denominators and adding is something that can be productive sometimes. And since we have two big fractions here, that's just, again, the low-hanging fruit. Don't be afraid to go for the low-hanging fruit. So to get common denominators, I'm going to have to multiply both fractions by something. Okay, how do I get these denominators to match? Well, it's going to have a factor of cosine of t. It's also going to have a factor of sine, 1 plus sine of t. So over here, this is the fraction that needs the factor of 1 plus sine t. So I'll multiply top and bottom by 1 plus sine of t. Over here, I just have to multiply top and bottom by cosine of t. Okay, it looks like a mess, but let's just do it. Oftentimes, these problems get worse before they get better. Let me just make sure I have my grouping symbols here so I don't make any mistakes in multiplying these together. When we're multiplying fractions, we multiply straight across. So this first fraction will be 1 plus sine t times 1 plus sine t. Make sure I have my grouping symbols there, over cosine t times 1 plus sine t. Over here, I'll have cosine t times cosine t over cosine t times 1 plus sine t. Okay, so my denominators are now matching. That's good news. That means I'll be able to add these together eventually. Before I do that, I might multiply these out, the numerators, that is. The denominator I'm going to leave factored. You know, oftentimes it's best to have the denominator in factored form. So I'm going to start by multiplying out the numerators. Here I'll get 1 plus 2 sine t plus sine squared t. Okay, and that was foiling that out. Okay, I had to FOIL out. So however you do that, if you do the first, outer, inner, last thing, I know some people like to do the box method like this, where here you have 1 plus sine t and 1 plus sine t. So however you like to do it, totally fine by me, whatever works for you. All right, and then over here, whoops, I will just have cosine squared t, and over our common denominator of cosine t times 1 plus sine of t. Okay, now I definitely am nervous about this. Like I'm putting in a whole bunch of work here. I don't know if it's gonna work, but you just kind of have to be brave and be patient. Just have the courage to try something. Let's see what happens here. Okay, we're gonna now add these two numerators together and put them over our common denominator of cosine t times 1 plus sine t. Still undecided whether I'm gonna multiply that out. I'm just waiting for now. And I get this 1 plus 2 sine t plus sine squared t plus cosine squared t. Okay, I am seeing a glimmer of hope in this problem. Maybe you recognize this as well. Sine squared t plus cosine squared of t. I'm so happy whenever I see a sine squared plus a cosine squared show up in one of these problems, because that is just going to become a 1. So now I'll have 1 plus 2 sine t plus 1. How nice is that? That helped a lot, I think, I hope. Over cosine t, 1 plus sine of t. Okay, I can add 1. I'm going to keep working over here. I'll add 1 plus 1, and that will give me 2 plus 2 sine t. Denominator still unchanged. Okay, and I'll pause here and just sort of look back, like, what am I aiming for? Remember, I'm aiming for 2 secant t. It might not be too obvious that we're headed in that direction, but I am seeing that there's this factor of 2, this shared factor of 2 in the numerator. So, okay, let's pull that out. I can write this as 2 times 1 plus sine t. Okay, just factoring that. And all of a sudden, I'm feeling very optimistic, because look, we have a common factor of 1 plus sine of t in the numerator and denominator. So we can cancel that out. That gives us a big 1. And we are just left with 2 over cosine t. This is looking really good, because cosine t in the denominator can come up into the numerator as a secant. This is just 2 secant t, which is our right hand side. We did it. I'll do my little filled in box down here. Identity has been verified. Okay, that was a really messy one. It required us, notice how many of our skills from college algebra and before we have to be employing in these problems. Like, these problems are so challenging because it's really the sort of intersection point, the collision point of all these different topics, all these different skills that we've been building for so many years. And now we have to really carefully apply all these skills to simplify these complicated expressions, in this sort of attempt to verify these identities. So, work really carefully. Don't be surprised if you have to multiply out some binomials or factor. There are going to be trig functions involved, which is a little confusing. Maybe this is the first time you've had to multiply out a couple binomials that involve sine of t. But just go with it. If it starts to look like it's a dead end and you're really not confident in what you're doing, and you're not getting any closer to the right-hand side or the left-hand side, whichever you're shooting for, you can scrap it and try something else, but oftentimes the follow-through, if you just follow through with what you're trying, eventually you'll sort of see these desirable outcomes. Okay, so that's a great example to study from. Let's try another one. Sorry, I don't know why my document keeps dropping my inputs for my trig functions here. I'll make sure to fix that for your document. Example 4, we want to verify this identity, cosine theta over 1 minus sine theta. This should be equal to secant theta plus tangent theta. Now I know this looks a lot like example 2. It isn't quite the same. Here we had 1 plus sine x over cosine x. This one we have cosine over 1 minus sine. So let's try this. How about we start with the left-hand side this time? So let's start with cosine theta over 1 minus sine theta. And see what we can do to manipulate this to hopefully, so I'm aiming towards secant theta plus tangent of theta. Notice that this is a sum. We have a plus sign in the middle. There are two terms. How might I break up this fraction here into two terms? Notice that the subtraction here is happening in the denominator, which is not really what we would want to see. Remember, if we have plus or minus in the numerator, we can break up the fraction. That's like what we did over here, right, in this first step in example 2, the sort of second version of this problem. We started by breaking it up, but we could do that because this addition was in the numerator. Now here we have subtraction in the denominator. There's a really helpful trick which we can use sometimes, especially if we have something like 1 minus sine of theta. I can multiply top and bottom of this fraction by what we call the conjugate. Okay, and the conjugate, this concept of a conjugate has popped up many times. It shows up in college algebra quite a bit. You might remember if we have something like this. Okay, totally separate type of problem, but if we were trying to simplify or rationalize this denominator, we have 1 over 1 plus 3. Sometimes we would multiply by a conjugate here. We would multiply by 1 minus root 3 on top and bottom. Okay, and the reason we do this is because when we multiply these together, in the numerator we would just have 1 minus root 3. In the denominator we would have to FOIL it out, and we would get 1 plus root 3 minus root 3 minus root 3 squared, right? So that was just foiling it out. And what happens here is we get 1 minus root 3 in the top, and notice that positive root 3 minus root 3, those are opposites of each other, so they cancel out. So we get 1 minus root 3 squared, which is just 3. Right, so we end up with this, 1 minus root 3 over negative 2 in this case. Okay, so you're probably wondering, why am I rationalizing denominators right now? Well, right here what we did is we multiplied by the conjugate. Okay, and what the conjugate is it's just like, take this denominator, change the sign, the sign of one of the terms. And if you multiply by that conjugate, you'll get some kind of, nice cancellation. The denominator simplifies to a rational number. We can use a very similar technique here. I'm going to multiply by the conjugate of the denominator, which is going to be, again, just change the sign of one of those terms. How about let's do 1 plus sine theta, okay? And I have to multiply top and bottom by the same thing. That's the only way that this works. Okay, and let's see what happens here. So up top, I'll have cosine theta times 1 plus sine theta. Don't forget the parentheses there. In the denominator, 1 minus sine theta times 1 plus sine theta. And if I multiply out the denominators, and also I could do the numerator as well. So in the numerator, I'll just distribute the cosine. I'll get cosine theta plus sine theta times cosine theta. I could just leave it as a product like that. And in the denominator, foiling it out, I'll get 1, let's see, so that's first, outer will be plus sine theta, inner is minus sine theta, and last is minus sine squared theta. Okay, what happens is these two middle terms in the denominator cancel out, and I'll have this. One minus sine squared theta. 1 minus sine squared theta is actually a really nice thing. This is something that you'll learn to be really happy to run into. And here's why. Remember, we have this Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. I can subtract sine squared theta from both sides and I get this. Cosine squared theta is equal to 1 minus sine squared theta. Okay, so what I'm going to do is I'm going to use this, particularly this right here, and I'm going to make that substitution into the denominator of my equation. So now I'll have cosine theta, again, sine theta, cosine theta, but I'll substitute in for 1 minus sine squared theta, cosine squared theta. Okay, so the two main tricks we've done so far is, just to write it out, we multiplied by the conjugate of that denominator. And then we made this substitution using the Pythagorean identity. Just a slightly modified version of the Pythagorean identity. Okay, so now you're probably wondering, okay, does nice stuff happen yet? Usually we get to a point in the problem where nice stuff happens. Yes, I think so, because now that we have the plus sign in the numerator, we can split up this fraction. Get cosine theta divided by cosine squared theta. I am feeling optimistic about that term. Plus sine theta over cosine of theta over cosine squared theta. And now here's where the good stuff happens. We have a common factor of cosine theta in this first term, so it simplifies to 1 over cosine theta. Love that. Over here, again, another common factor of cosine theta, so this simplifies to sine theta over cosine theta. And look at that, that gives me secant of theta plus tangent of theta, which is our right-hand side. Yay. Okay, so multiplying by the conjugate, something that you might want to try if you see some opportunity to get a Pythagorean, kind of difference, like 1 minus sine squared theta or sine squared theta plus cosine squared theta, something like that. This is worth trying, and it worked out in this case. Is this the only way to do this problem? Probably not. But I did it, I stuck with it, and I got there in the end, so I'm happy about it. Not going to bother saying the whole equation here. I'm already losing my voice a little bit. Let's just start strategizing. So do I want to start on the left side and maybe put everything in terms of sine and cosine using those quotient properties, or maybe I could start on the right-hand side, and I see the sine squared t. Maybe there's some Pythagorean kind of opportunity there. I'm thinking that it's going to be a lot harder to start with this and end up with that crazy quotient there. So I think I'm going to start with the left-hand side and see what I can do there. So the left-hand side, and yeah, cotangent and tangent, not my favorite trig functions to be working with. Let's try getting this all in terms of sine and cosine and just see what happens. See if anything kind of, any opportunities pop up. So cotangent is the same as cosine t over sine t, minus tangent, which is sine t over cosine t. And then in the denominator, cotangent, again, cosine t over sine t, plus tangent, which is sine t over cosine t. All right, a bit of a mess, but we'll just work with it and see what happens. Now, what would be a natural next step from here? Kind of the only thing that I could think of doing really is trying to add those fractions together in the numerator, add those two fractions together in the denominator, in the big denominator that is. So if I'm going to add these two fractions together, I'll have to get common denominators, and it'll have to include a factor of sine of t and also a factor of cosine of t. So here's what I'll have to do. I'll have to multiply this one by sine t over sine t, and this fraction will get multiplied by cosine t over cosine t. All right, and same kind of thing is going to happen in the denominator. I'll write my next line a little bit larger so it'll be easier to read my handwriting. It's getting a little cramped here. All right, now let's do that. So in the big numerator, that first fraction will be cosine squared t over sine t times cosine t. And then minus over here, I'll have sine squared t over sine t cosine t. So that's good. I have my common denominators up there. Now looking to the bottom of the big fraction, I'll have cosine squared t over sine t cosine t. And now plus sine squared t over sine t cosine t. And now with those common denominators all over the place, I can add together in the numerator, and I'll get this cosine squared t minus sine squared t over sine t cosine t. And in the big denominator, I'll have cosine squared t plus sine squared t. over sine t cosine t. Okay, so here's my big numerator, here's my big denominator. Something good better happen soon because I'm tired. But I see something that I like. I see cosine squared t plus sine squared t. Addition is commutative, right? This is the same as sine squared t plus cosine squared t. I can replace that with 1. Okay, and is there anything else good going on? Not really. I don't see any other obvious substitutions to make right now. Let's just leave everything else as is. So the numerator is going to stay. Right, that's not going to change. But down here we'll have 1 over sine t cosine t. So we'll have this now. All right, and at this point I have, a fraction in the denominator. Remember, I can just multiply by the reciprocal of that. So I'm going to do that in the next step. So then I'll be out of the fractions inside of fractions scenario, which is a difficult one to be in. So I'm glad that we're sort of emerging from that fog. And now we're multiplying by sine t cosine t over 1. Okay. And the good news here is we have now this common factor, or 2 common factors, sine t and cosine t in the numerator and denominator. So those will go away. Keep working up here. And let's see what we're left with. We're left with cosine squared t minus sine squared t. Okay, and another look back at what we're aiming for. We want to get to 1 minus 2 sine squared t. So we already have 1 negative sine squared t. I am hoping to get another negative sine squared t to pop up. So I'm looking at this cosine squared t and thinking, what can I do with this? Well, whenever I see a cosine squared or a sine squared, I know that the Pythagorean identity could come into play, right? Because remember, the Pythagorean identity for sine and cosine is sine squared t plus cosine squared t is equal to 1. So I'm wondering if I might substitute something in for cosine squared t. Let me solve for cosine squared t in the identity. And I'll get 1 minus sine squared t. Okay, so I'm thinking about substituting in for cosine squared t 1 minus sine squared t. And I'm feeling pretty good about that because that gives me the 1 and my extra negative sine squared t that I'll need. And that will bring me to 1 minus 2 times sine squared t. And we've done it. We have reached the right-hand side. So we have verified this identity. Okay, so like I keep saying, just if you see a path forward, don't be afraid to chase it. And it might get messy. It usually gets worse before it gets better, and we definitely saw that in this one. This is a pretty wild expression right here. But if you stick with it, you might find that good things happen. And if it's really looking bleak, you can always scrap it and try something different. But this is a great example of where just trying something and being persistent can get you there in the end. And that's the last example for this section. This is a very challenging section, just getting used to, working with these identities, verifying these. We have to be really on top of our trig identities, on top of our algebra skills, factoring, dealing with fractions. This really is the intersection point of a lot of skills that we've developed in, recent years of our math education. So these are all great problems to study from. And going forward, we're going to be introduced to a few more identities and formulas. And we'll definitely see more of these verify the identity type problems in the upcoming sections. So I'll see you in 9.2 where we talk about sum and difference formulas.